Hello, 8th graders. Today we are going to go over Chapter 2 in the Geology iBook that I have posted on the Google Classroom. Okay, so you don't need to follow along in the book on your iPad, just watch this video, okay? So yesterday we talked about what a mineral is, right? Chapter 1 was about minerals. We learned that they are inorganic, they are naturally occurring, they are solids, they have a definite chemical composition, they have a crystal structure, right? Today we're going to figure out how scientists can pick up one mineral and be able to use its physical characteristics in order to correctly identify that mineral. And this might seem overwhelming with information, but it's going to make a lot more sense once I get back and we can do this ourselves. You know, I've got a classroom set of minerals and we'll be going through these tests ourselves for you to be able to correctly identify some of them. All right, so this is just kind of an introduction to mineral identification. Let me scroll forward to Chapter 2. And it starts out with this beautiful sample of a mineral. One thing that scientists are faced with, you know, any field of science, whether it's mineralogy or entomology, which is the study of insects, or ichthyology, which is the study of fish, or ornithology, the study of birds, is that there are thousands and thousands of different organisms that scientists need to be able to identify, and they don't just memorize them all. That would take way too much brain space, and there's really no need to do that if we can look at physical characteristics and use something called a dichotomous key in order to correctly identify something, okay? And this is no different with minerals. We look at physical characteristics and we use process of elimination in order to narrow down the possibilities and correctly identify them, all right? So a couple of those things, just to quickly introduce it, it says, check out the mineral above. How would you figure out what kind of a mineral is? Would you look by color, by shape, whether it's shiny or dull? Are there striations, like these little lines right here? Is it shiny? Does it have cubic crystals? Does it smell? Does it taste? And by the way, we're not going to be tasting anything in my classroom because that's gross. If you're out in the natural world, then yeah, taste is actually a really valid test to do with some minerals. Some minerals taste very sweet. Some of them taste very bitter. Some of them taste salty, like rock salt is going to taste very salty. All right. So we're just going to quickly go over some of these physical characteristics. And again, when I get back and we do this hands-on, it's going to make a lot more sense to you. Okay, it says there's a multitude of laboratory and field techniques for identifying minerals. While a mineralogist might use a high-powered microscope to identify some minerals, or even techniques like X-ray diffraction, most are just recognizable using physical properties, just by observing them, just by looking at them. The most common field techniques put the observer in the shoes of a detective. Again, you are using process of elimination. You're starting with an unknown and you're asking yourself some questions, a series of questions in order, and you will eventually eliminate a bunch of minerals and really kind of hone in on one or two possibilities. Okay, the process of elimination usually includes observing things such as color, hardness, smell, solubility in an acid, streak, striations, and or something called cleavage. And I'll give you a second to giggle about that one. All right, so color is one. Now, color alone can't be used to identify a mineral, and here's why. This picture right here, these are both quartz. Quartz comes in every color of the rainbow, and there are many different minerals that come in the same color as well, okay? So color should always be used kind of at the end. After you've gone through a series of tests, the last thing that you can do if you're trying to distinguish it between one or two minerals is use the outward appearance of color. Color alone can't be used by itself. Another reason is that exposure to UV radiation, sunlight, or exposure to prolonged water, that can change the color of a mineral. And so it is kind of misleading. Color can be a little bit misleading. So color needs to be used alongside some other tests. Streak is a very, very good test to do with the mineral. Streak is the powdered form of the mineral. So when we get back to class, you guys will have these little streak plates. You'll get a porcelain one, a white little cube, and a slate streak plate. And when you drag a mineral across those streak plates, the powdered form makes a line, just like sidewalk chalk would on a sidewalk. Well, different minerals that have different colors, if it's the same mineral like quartz, it comes in all of these different colors, but the powdered form of it will always be the same. So you can have a mineral that is, you've got a white sample, a gray sample, and a black sample. When you streak them across a plate, the powdered form will always be the same color, okay? So streak is a really good test to use in combination with all of these other tests, all right? Luster is one of the first questions you're going to ask yourself. Is the mineral metallic? Does it look metal-like? Or does it look glassy? Does it look pearly? Does it look like resinous, like tree sap? Does it look soapy or kind of fibery? Its luster is defined by how it reflects light, but really it is, I remember it as luster is kind of, what does it remind you of? You know, of the known things in the world that you are aware of and you are familiar with, what does it remind you of? Does it remind you of some kind of a metal? Does it look rusty? Does it look like steel? Does it look like glass? Does it look like a pearl? Okay, so the luster is really how it appears and what you can relate it to of, you know, known things in the world. Density. Density is, you guys should have learned this in 6th grade, but density is how tightly the atoms of a mineral are packed. Okay, so imagine you've got a mineral in each hand and they're the same size. Okay, they're the same size, but one is much heavier than the other. Okay, that means that the atoms of that mineral are more tightly packed and it is denser than the other one. An example would be like lead. Imagine holding a handful of lead in one hand and a piece of pumice or volcanic rock that has a lot of air bubbles in it. It's really, really light, so light actually that it floats in water. Those two have very different densities. Even though they might be the same size sample, one is a lot heavier, okay? So density, we're not going to get into a lot of detail with density, but you should be able to know this particular physical property will come into play when you've got like a really, really noticeably heavy mineral or a really, really noticeably light mineral, okay? Those are the only two that we're really going to be using this one for. Hardness is one of the best physical characteristics to narrow down the identity of a mineral. And tomorrow's lecture is going to be specifically just on using something called the Mohs scale of hardness. Some dude with the last name of Mohs came up with this hardness scale. And I'm going to teach you that tomorrow in lecture, and there'll be a little activity there. We're going to be practicing this a lot in class too. It's kind of a hard one to learn in class, especially with our classroom set of minerals, because they've been scratched and tested so much over the years that sometimes it's difficult to know if when you're scratching it with your fingernail, if it's just the powder coming off from a previous test or if you're actually scratching it. But the Mohs scale is a hardness scale from 1 to 9. 1 being really, really soft, like you could scratch it with your fingernail, almost like soapstone. Like if you picture a bar of soap, you can easily scratch it with your thumb, right? And then something really, really hard, like a 9 or a 10 would be a diamond. You're not going to be able to scratch that with your fingernail, nor do I have any diamonds for you to try that out with. Okay, so don't get any ideas. We go through a series of tests to be able to determine what rating on the Mohs scale each mineral has. Okay, and I'll get into a lot more detail with this tomorrow. The Mohs scale has these numbers here, and then they have an example of the minerals that are these hardness. Like talc is really, really soft. Talc is also known as soapstone. Gypsum is a little bit harder. Gypsum is the mineral that is in sheetrock. You know, you can picture sheetrock. You can scratch that with your finger, right? Quartz, you guys know what quartz is. Quartz is a mineral that makes up the bulk of like granite. It's the sparkly stuff. That's really, really hard. Okay, you're not going to be able to scratch with your fingernail, but you'll be using some other tools to see if you can scratch that. All right. So these are just examples. If you get a mineral and you determine that it's a 4 on the Mohs scale, that doesn't mean that it's fluorite. Fluorite is just an example of one mineral that rates as a 4. There are many minerals that rate as a 4. All right. And this will make more sense tomorrow when you see my lecture. Cleavage and fracture. All minerals have a crystal structure. Their atoms are arranged in some way. And in some minerals, the atoms are arranged in 90-degree angles. They're arranged in like a cube. They're arranged side by side by side and then down, and it's just like reading a book. Well, what happens there is if I were to take one of those minerals that have that 90-degree atom structure and smash it with a hammer, it's going to break off in sheets like this. It's going to break off in straight edges, 90-degree angles. That's called cleavage. To cleave means to split. So there you go, a little tidbit of information. The other option is called fracture. Okay, so like quartz does not have that alignment of atoms. So if I took a hammer and I smashed a piece of quartz, it's going to break off in like random chunks. So for our purposes in our class, we're just going to be worried about, does the mineral have cleavage? Does it break off in sheets? Or does it have fracture? Does it break in random chunks? Okay, if you take a geology class in college, you can get way into detail about like in how many directions, how many angles does it break off. We're not going to really worry about that because, again, the samples that we're using have been tested so much that it's a little bit difficult to see, but you will be able to tell if it has cleavage or fracture. Okay. Here's an example of mica. Okay, sheets of mica. We can find this all over, like, if you've ever been to Blanchard Dam, you'll find the mineral mica all over in that area. You'll find little flecks of it all over. It's really, really shiny, almost looks gold-like. And then sometimes you can find a big chunk of it, and it's called a book of mica, and you can actually peel it off in sheets. This is an example of cleavage. Okay. Here's another one. Magnetite has these straight edges that it breaks off on. And then there are all of these other kind of cool identifying characteristics. Certain minerals have really unique characteristics. For instance, fluorite, if you shine like an ultraviolet light on it or a black light, it'll actually glow, like it'll fluoresce. Magnetite is magnetic. Calcite, we'll be able to do this test in class too. If you drop a little bit of a weak acid on it, a hydrochloric acid, it'll bubble. Okay, so that calcite actually looks a lot like a couple other minerals, and they have all of the other same characteristics, physical characteristics. They have the same hardness and the same color and all of that. And then the only way to tell is that one final test. You put a drop of acid onto the one that bubbles, you'll know is calcite. Smell is another one. Sulfur definitely smells like matches or like rotten eggs. And then halite is, the common name is rock salt. Obviously that one is going to taste salty. And again, we will not be tasting anything in my class, mainly because I've said that every year and there's always somebody who does. And so if you taste anything in my class, you can be sure that somebody else has licked it and that's gross. Okie dokie. Well, that is a very quick overview. Again, it's a lot of information, I know, but we are going to be looking at each of these physical characteristics together in class, and it's going to make a lot more sense when you're going over this and you've got a bucket of mineral samples in front of you. And I can say, pick up sample number 1 and look for this particular characteristic, okay? And we'll do that next week, all right? So don't worry too much about the details here. I just wanted to introduce these physical characteristics to you. Now your job today is there's a few questions, 5 questions that go with this video here. Again, if you go back to your Google Doc that I posted on Monday, we did chapter 2 today. Okay, so you're going to go to chapter 2 on your Google Doc. You can click, boom, on this little link right here, watch this little video, and answer these questions on chapter 2. Sound good? If you have any questions, let me know. Any remaining time today you can use to work on your landform project. Okay, yesterday you were to have chosen a landform from the list. Today you can start researching on the Google Slides. Start doing a little bit of internet research and finding out the location of the landform that you chose and how that landform was formed through natural processes. And we will talk again soon.